damped system, if you have a resistivity in your system, the force does not equal the acceleration, equals the velocity, right? If you have damping, the force equals the velocity. If you solve a damped harmonic oscillator, the force equals velocity. So the very fact you can write this force equal acceleration. It already tell us you consider this system has no resistance, no resistivity, no damping. Okay. Then if you combine these two equations, you can get that the magnetic field, once it enter into a superconductor, magnetic field will be exponentially decay inside superconductors. If you combine these two equations. So this is the London equation. So our question is that whether you can write a similar London equations, similar equations for spin superconductors. It turns out you can do that. So in a charge, the force equals Q times electric field. If the spin superconductor, we have a spin. Spin is basic, it's a magnetic dipole, right? So the basic force from magnetic dipole in the presence of, in the presence of a magnetic field or gradient, it appears in this form. It appears m dot gradient of magnetic field. So you have a gradient operating from the magnetic field. So once you have this, you can derive that what is the spin current density, what's the time derivative. You will find there's these two equations. Okay, these two equations. So again, spin current density, time derivative, and the Q of spin current density, that's these two equations. So if you compare with the London equations for the charge current, first is electric field and magnetic field interchange the places. Okay, in the previous equation, here is electric field. The time derivative has electric field on the right. The Q of current density has magnetic field on the right. And here you have exchange, electric field, the locations for electric field. The other thing is that due to this force has gradient, it's not just electric magnetic field, it's the gradient, this term, gradient, S basically a magnetic dipole. It's the gradient of this appeared. So if this equation, we know that in a charged superconductor, you will screen the magnetic field. Then from these two equations, you can see you will screen the electric field. Also, it's not just the electric field, it will be screen the electric field, gradient of the electric field. So in a spin superconductor, you could have a uniform electric field or zero electric field. You will screen the gradient of the electric field. Again, it's consistent with what we talked about at the beginning. If you have a spin motion, it will create electric field. So again, in a spin superconductor, you will also screen the electric field or the gradient of the electric field. And we look at one example of this. Suppose you have a ferromagnetic graphene, which gives you a spin superconductor. You put a charge somewhere nearby this ferromagnetic graphene, and the presence of this charge will create an electric field on this ferromagnetic graphene, right? Electric field on this ferromagnetic graphene. Okay, and through the through this equation, the gradient of this electric field due to the extra charge will give you the spin current, okay? And will give you the spin current. Then remember, once you have a spin current, the spin current will also create its own electric field, right? I mentioned at the beginning of my talk, the spin current is the source for the electric field. It will create its own electric field. And it turns out these two electric fields will cancel out. One is the blue curve, one is the black curve. In your spin superconductor, these two electric fields will cancel out. Okay. So this is one of the examples of that you have a so-called Meissner effect. And later on, my student Zhibo Wang also did a calculation for other geometries. Once you have a spin superconductor, how it screen out the gradient of electric field. So he's in the audience here. For those of you who want to have a more detailed discussion, maybe we can talk to him, okay, on this part of the work. Then let's also talk about try to look at another important effect of a superconductor. In charged superconductor, we have a Josephson effect, and the spin superconductor, turns out they have the similar situations. So if you have two spin superconductors connected by a normal conductor or insulator, then you could have a Josephson tunneling in your systems. And again, the current is the spin current, okay? And you just need to have let me skip this. You just need to have the phase difference between these two pieces of the spin superconductor to give you a Josephson current, okay? Josephson current. Now, if you look at the history of charged superconductor, one important breakthrough is the Landau-Ginzburg theory for a superconductor. Similarly, we can write down a Landau-Ginzburg free energy, a theory for a spin superconductor. So basically, as I mentioned in the beginning, so if you have a spin orbital interaction, it contributes another term in the canonic momentum term due to spin orbital interaction. If you put this term in, okay, that will give you the basic piece for free energy. Then if you derive this free energy, you have two equations basically, and they'll give you two equations which give you the same result as you derive from the Lambda equations. Okay. So you do have a Landau-Ginzburg series for spin superconductor. Yes.
I wonder what the other parameter is that.
Well, it's the also the gap, as I mentioned. You also have a gap opening up. So the gap is also the order parameters for this. Yeah. But it's yeah. Now, in the remaining maybe a few minutes, let me try to discuss how do you experimentally detect this spin superconductor. Suppose you already have a spin superconductor, how do you detect spin superconductor? And let me tell you, at the beginning I tell about one way of detect spin current. It's through the so-called spin Hall effect. Okay, spin Hall effect. Okay, so if you have a spin orbital system, then if you apply electric current in one direction, in the direction vertical to the current motion, there will be a spin current motion, and you can detect spin current. Then there okay. Then there's another way of detect spin current. It's so-called non-local resistance measurement. Non-local resistance measurement is pure charge transport measurement. Okay, but it can also detect spin transport, spin motion. Okay. So what's the basic setup of this non-local resistance measurement. So suppose you have a device, okay? In this device, it could have a spin transport. So basically, you can call it spin metal. Spin can pass through, okay? And whether charge can pass through or not is not important. So it probably it's better if charge cannot pass through, so okay, but the spin can pass through. Okay? If you have a charge insulator, but a spin conductor, spin metal. Now, if this is the case, you can have suppose this is a sample. You have two ferromagnetic contact at one end of the sample, and another two at the other end. So these two contacts create electric current loop. Okay, so you send the current through this loop. Okay, so electric current is at this loop. Okay, then if this, since it's a ferromagnetic contact, it has it can also make spin excitations. Okay? So once you have spin excitations, although there's no charge current pass through, the spin current can pass through this system. Okay? If this is if in terms of spin, it is metal, it's a conductor, so spin can pass through. Although there's no charge pass through, the spin can pass through. If a spin can pass through, this voltage, you can also measure it. There's a finite voltage, non-zero voltage. So this voltage divided by this current give you so-called non-local resistance. So this is also one way of measure spin current. Okay. So you have a charge current loop here, you have voltage loop here, and if there's spin pass by, you can measure this spin non-zero resistance. Okay. So we propose if this device here is a spin superconductor, then you will have some signals here. And first, if this setup, if we just measure the normal resistance on the two ends of your spin superconductor, because I mentioned there's an energy gap opening up once you have a spin superconductor. So this energy gap opening up in terms of charge transport is a metal, or it's an insulator. So if you just measure this resistance as you lower the temperature, at a low temperature, when this gap opening up, this resistance, this between 2 and 3, these two contacts, will just show the property of a normal insulator. As you lower the temperature, you will have your resistance goes up quickly, just like normal insulator, normal semiconductor. Okay. That's first indication that you have maybe opening up of a gap, you have an insulator here. Then you can measure this local resistance. And the non-local resistance will be, although it's a pure charge measurement, they have flat regions. Okay. These flat regions tell you spin in terms of spin transport. It's a perfect spin conductor. So if we combine this, there's a strong possibility that you are entering the region of a spin superconductor. So far the proposed system is a ferromagnetic graphene. As I mentioned, there's still experiment is still going on, trying to achieve that. Okay, ferromagnetic graphene. And our proposal is at this stage. What I mentioned to you is purely depends on you have to have ferromagnetic graphene first to have a spin superconductor. But it turns out there's another system which we think may already have some signal of a spin superconductor, which is already experiment realized system. What is this system? It's this graphene under strong magnetic field. Okay. Basically, it's a quantized Hall effect system of graphene. right? Graphene on the strong. So this not the graphene is just normal graphene. It's not a ferromagnetic graphene. Okay, just normal graphene. But if you apply strong magnetic field, then this is the without magnetic field it's just direct cone. With the magnetic field, this is the diagram for graphene on the magnetic field. And importantly, it has this picture here. Okay, so you have two values. Okay, so value we use value. The graphene has values. We use plus and minus, and the spin use this arrow, up and down arrows. Okay, and let me show you the experiment findings first. Okay, the experiment. So certain graphene, high mobility graphene on the strong magnetic field. Of course, you see a quantized Hall effect. You have a quantized plateau. Okay. So the jump of the plateau is from 2 to plus 2 to minus 2, 2 to 6, by always as a factor 4 due to spin degeneracy and value degeneracy. So you have a factor 4. Okay. If a normal semiconductor, normally it's a 2 if you have spin degeneracy, but this is a 4. There's a 2 to 6 and so on, or for minus 2. Here, minus 3 you have a whole band and you have 2. But importantly, it's at the direct point, at the zero neutral point. Some of the experiment, not all the experiment, so it depends on the sample quantity, has a small plateau, region, very small plateau. Okay. However, there's a strong difference between this plateau and the normal quantized Hall plateau. In the normal quantized Hall plateau, once you have a plateau, the longitudinal resistance goes to 0. Okay. Goes to 0, like here, goes to 0. However, at this small plateau, longitudinal resistance goes to very large. If you reduce the temperature, it goes up. So in fact, it's a peak. Because as you lower the temperature, it goes up. So just from this longitudinal resistance, you can tell it is an insulator. It's not quantum Hall state. Quantum Hall state, in some sense, is a perfect conductor, because along the edge, because the resistance Rxx goes to 0, right? So it's perfect. But here it goes to it's very large peak. Okay, so it is insulated, but it still have a plateau. Plateau normally tells you opening up a gap. Okay. So this experiment, the other experiments, let's see. Yeah, there are other experiments. Different group has other experiments. And another thing is that they also did a non-local measurement, non-local resistance measurement on this system. So at where you see this small neutral point, where you see plateau, the non-local resistance is not 0. So that means there's some non-charge system, non-charge transfer, and very likely spin transfer passes through. Okay. So if we combine all these results together, we believe it is this situation. Okay. So the situation is drawn by the diagram I have here. So this is the band structure, and very similar as what we had for ferromagnetic graphene. There's a crossing point for the whole band and the electron band. Okay, whole band electron band, and due to the Coulomb interaction, attractive Coulomb interaction, at this crossing point, you will open up a gap. Once you open up a gap, the story could be pretty much like what we had. You will have an insulate, but below the gap is a spin superconductor. Then if you accept this explanation, you can understand all the experiments First, it's charge insulate. That's why you have a peak. And the second, because it opening up a gap. Because spin superconductor has a gap. That's why you have a plateau. And the thirdly, it has non-local resistance as a spin transport pass through. Okay. So we believe that it could be already some indication that this experiment, people try to understand, couldn't find a satisfactory understanding. But if we accept this concept of spin superconductor, seems to be you can understand all the experiment findings. So this is the. So let me make a short conclusion that we predict as a spin superfluid or spin superconductor in ferromagnetic graphene, and this spin superconductor carries a dissipation as a spin current, okay, at equilibrium. So it is the ground state problem. And we also propose PCS type theory or the non-principal theory, and we discuss the so-called Weisser effect in this system. Basically, you can screen the gradient electric field. Okay, thank you for your attention.
Thank you for this interesting talk. Any questions?
Okay.
Thanks a lot for a very interesting talk. I have a question about the realization of your device, the proposed device leveraging a non-local spin valve. Now, graphene is a pretty good spin conduit anyway, whether it's superconducting for spins or just has a large spin diffusion length and so on. So you are going to get a non-local signal, whatever. Not only if you're in the superconducting state.
Yes, that's why you have to combine with other experiments. Like I mentioned, not just one experiment. So you have to combine. First, you have to be a charge insulate. So normally, if you just have the crossing, it's not a charge insulate. You have carrier at the crossing point, right? So what I'm saying that it has to be charge insulate.
So you not only need.
Yeah, you have to combine all these. It's just graphene is a good spin transport device because no spin orbital interactions. So
high mobility.
Yeah. So, but you have to combine. So what I'm saying that you have that's energy gap opening up here. So it's charging insulate to start with. Then you have to if you do a measurement as what we suggest here. What we suggest here. So you should also see this curve.
Yeah. So you see a jump when you hit
jump.
the superconducting temperature.
That's right.
Okay, thanks.
I was wondering, how do you grow the graphene on the ferromagnet?
How do I grow the graphene on ferromagnet? I'm not the experimentalist, but there's a candidate. There's a proposed system. It's EU oxide, which people tried to grow EU oxide. Apparently, a ferromagnet insulate system, and then there are some first principle calculations, and try to see whether you can sort of energetically or lattice match and those problems. And it turns out, according to that calculation, that it's a good ideal candidate as the ferromagnet insulate to grow the graphene on. So then the recent experiment I heard, they claim they already see ferromagnet graphene. It's not on EU oxide. I forgot, it's different system. So there's Professor Xie from UC Riverside. He has a system. I forgot exactly what system it is. He claims he has some indication of seeing a ferromagnetic graphene.
Okay.
In charged superconductors, important evidence for detecting superconductivity, especially for the instruments like STM, the the magnetic vortex is a very important evidence, and it's very counterpart in spin superconductor.
Yeah, very good question. First, like STM, I think the problem here is that, as I mentioned, once it's a spin superconductor, it's charge insulated. So normal STM may not work. So that you have no, it's hard to have tunneling current pass through if you have a charge insulated. But your question is about this whether you have like vortex structures and so. So you have to then go to that's type 2 superconductors. So here it turns out we believe that probably you probably cannot define this concept type 2 in this system. That's the understanding at the moment. Yeah.
More questions?
I would like to clarify two things. So the first, the Meissner effect and Josephson effect, is that a general for spin superconductor or just for ferromagnetic graphene? Or
It's general.
it's very general.
Yeah.
And the second is the zero energy lambda level, and you will see a longitudinal resistance. So that is a non-local measurement.
The longitudinal resistance it's not what we call the non-local resistance measurement. It's just the normal set the longitudinal normal setup is like a 4 pro measurement or 6 pro whatever. Longitudinal resistance. Let me see whether I have a picture of the measurement setup. I probably don't have a measurement set. Well, that's it's not clear. I guess here could be the sample, like these two contacts. So the RX-axis is just measure these two. You have current pass through, then you have voltage difference between these two. So here is the sample. You have a current pass through these two contacts, and then you have a voltage drop here. So RX-axis is just this. So it's just normal. It's not a non-local resistance. It's just because when you do a quantum Hall effect, it's just a normal 4 pro or 6 pro measurement.
So in the very beginning, you have mentioned that concentrates on the spin exciton triplet. So you emphasize on triplet that is spin 1 rather than the singlet of spin 0. So is there a special reason for that? What makes the difference?
Well, what makes is triplet instead of a singlet? It's just an energetic calculation. In this ferromagnetic graphene, it turns out they favor the triplet states have lower energy.
Just in this
Yeah.
ferromagnetic.
So like a normal graphene, if it's not ferromagnetic, people already say exciton, but the low energy configuration is the singlet.
More questions? Go ahead.
Since your starting point is charge insulator, right? In conventional or high DC superconductor, the Fermi surface always plays very important role. I mean, is your gap opened in the vicinity of the Fermi surface or the exciton?
That's right.
Since exciton is a bound state in the gap, so the electron density of states here is not very robust, so that your superconductivity maybe is not very
No.
easy to.
That's why we talk about ferromagnetic graphene. It's not a normal. I try to use the slides to tell the difference between our in ferromagnetic graphene. That's the before you turn on the